this video, let us try to understand about generated clock. So the command is create underscore generated underscore clock. So coming to generated clocks, most complex designs require more than one clock for its functioning. When there are multiple clocks in a design, they would need to interact or share a relationship. Asynchronous clocks are clocks signals that don't share a fixed phase relationship. So synchronous clocks will share fixed phase relationship, whereas asynchronous clock won't share it. Having only asynchronous clocks in the design makes it really hard to meet setup and hold requirements when multiple clock domains are interacting. Synchronous clocks share a fixed phase relationship. So remember this point. Synchronous clocks will share a fixed phase relationship, whereas asynchronous clock won't share. More often than not, synchronous clocks originate from the same source. Today's SoC, that is system on chip, contains heterogeneous devices within the same chip. This could include very high-speed processors as well as low-speed memories all on the same chip. These elements working at different speeds are usually triggered by different clocks. Each portion operating on its own clock would bring in asynchronicity in the design. This may result in several clocks being derived from one master clock. Such clocks are referred to as generated clocks or derived clocks. So simply these generated clocks or derived clocks are something that are derived from the master clock. These clocks can be generated in multiple ways. First one is it is clock divider, which is also called as frequency divider. Next is clock multiplier. It is also called as frequency multiplier. And the third one is clock gating. So this is the syntax: create underscore generated underscore clock. So this is the command, followed by switches -name, clock name, -source, from which source it is coming, and hyphen divided by. And we need to give the value, followed by the source object. Same thing is applicable, and here I am using multiply by. That is, you can go either with frequency divider or frequency multiplier. So create generated clock, name, clock name, -source, clock source, -multiply by value, or else you can give divided by, followed by source objects. And there is one more way, like you can also do it by means of edges. Create generated clock, name, clock name, source coming from clock source, followed by edges. That is rise, fall, and rise, followed by get pins. So you can see in detail here, this edges should be given like this. So the first value that you are writing here will be the rising edge, second one will be the falling edge, and the third one should be rise. That is, it should be first edge of the next clock period. So you will get clarity on this if you see some of the examples. Make sure you remember this. If it is hyphen edges, it should be rising edge, falling edge, and rising edge. Here the last one should be the first edge of the next clock period. I will show about this in the next slides. Now coming to the syntax. Syntax according to the design compiler, which is based on Synopsys tool. So this is the usage: create generated clock, -name, some clock name we need to give, followed by -source. It can be like port pin list, that is master source from which clock is generated. And next one is -master clock, that is master clock from which clock is generated. Next one -divided by, we need to give some divided by factor here. So generally frequency divider factor will be like it will be like multiple of 2, like simply which is the power of 2, followed by -multiply, like divide by or else multiply by, we can give some value. Next, duty cycle, we already know like duty cycle means the time period for which the signal is high divided by total time period. And -invert, this is used to invert the clock specifications. Next one is -pre-invert, this is pre-invert clock specification. Next, edges. In the previous slide I have shown you how to write for edges. Next, followed by edge shift, that is floating list of edge shift. Next, -add. Suppose if there are multiple clocks, then we need to use this particular switch called as -add. Next is -combination, that is clock source latency will derive from combinational parts only. So you need to understand about what is source latency and network latency. Next, -comment will give the comment, like you can give any comment for that, followed by the source object. So the source object can be the list of ports, or else it can be the pins. So this is the syntax from design compiler for create generated clock. Now see the syntax according to the genus tool, which is based on cadence. So simply go through this slide. Most of the switches and command will be same. So you can see the description of create generated clock. It creates a new clock signal from the clock waveform of a given pin in the design. So by using one master clock, we are generating the clock. So that should be given by using hyphen divided by, multiply by, and or else it can be given by means of hyphen combinational switch. So remember this note. This command must be specified with one of the following options. So these are those options. And hyphen add, I told you, like if there are multiple clocks, then you need to make use of this particular switch called as hyphen add. Please go through this particular text. It allows to specify multiple generated clocks on the same source with multiple clocks must fan into the source pin. If you omit this option and a clock was already defined on a pin or a port, this definition would override the previous one. Suppose if you are giving two different clock signals, and if you are forgotten to add this particular switch, then simply it will override the first one that you have given. Next, hyphen apply inverted. This should be given to the port, pin, or else hierarchical pin. It specifies the pin or port on which to apply the inverted clock waveform. So this is non-Synopsys Design Constraint option. Next, coming to hyphen combination, it restricts the path search for latency to only paths which do not cross sequential devices or the source pins of other generated clocks. Genus ignores this option for optimization and reporting purpose. Physical flow will honor it as part of Innova's initial placement. The write _ SDC command will write the option out for the consumption of downstream tools. Next, coming to hyphen comment. Comment means by using this you can give the comment. So if you want to divide the time period, you have to give this one. Next switch is hyphen divided by. Determine the frequency of the new clock by dividing the frequency of the source clock by this factor. So simply it will divide the clock with respect to the factor that you are giving here. If the frequency is divided by a certain factor, the clock period is multiplied by that same factor. Next, coming to hyphen domain, this specifies the clock domain to which the generated clock belongs to. Next, by using hyphen duty cycle, you will be giving the duty cycle. And hyphen edges specifies how much each edge specified with the hyphen edges option should be shifted. And next, coming to hyphen edges, this should be given as rise, fall, followed by rise. And hyphen invert. If you want to invert the resulting waveform, you need to use this particular switch. And this is the master clock. It derives the generated clock from the specified clock by using this particular switch. Next, similarly, like multiply by, followed by hyphen name is used to give the name, and hyphen source from where it is coming from. Now let us see the syntax according to the prime time tool. Please go through this particular slide. Just for your understanding, I have included syntax from all the tools. So here prime time is based on Synopsys, and this is the syntax according to the Tempest tool, which is from Cadence. Most of the switches will be same. Now let us try to understand what is divided by 2 waveform. So you can see here I have taken one waveform where here time period is 10 nanosecond. Now divided by 2 waveform means like I am dividing frequency by 2. As we know that frequency and time period are inversely proportional. So whenever you are dividing frequency by 2, time period will get multiplied. So you can see here, if I am taking a time period of 10 nanosecond and if I am doing divided by 2, then obviously time period will get doubled. So that's why you can see here time period is getting increased by twice. So initially time period is 10 and here I am getting time period of 20 nanosecond, which is simply the multiple of 2. Now let us see what is divided by 4 waveform. So if you are dividing frequency by 4, time period will get multiplied 4 times. Again I am taking the same example where the time period is 10 nanosecond. Now as I am doing divide by 4, so simply time period will be 4 times. So 4 into 10 will be 40 nanosecond. So here see the waveform that we are getting at the output will be having a time period of 40 nanosecond. Means simply it is divided by 4. Now let us see what is multiply by 2 waveform. You can see here if you are multiplying the frequency, time period will get divided. So initially the waveform that I am taking is having a time period of 20 nanosecond. Now here time period is getting divided by 2. So 20 divided by 2 will give 10. So the output waveform that we are getting will have a time period of 10 nanosecond. So first be clear with what is divided by 2, divided by 4, multiply by 2 and multiply by 4. So depending upon this, you can understand the next concept.
Now let us see in detail what is meant by clock divider. So clock divider is also called as frequency divider. That is, whenever frequency is getting reduced, time period will be increasing. Why? Because frequency is inversely proportional to time period. So if you are dividing frequency by 2, simply time period will get multiplied by 2. So coming to clock divider, which is also called as frequency divider. A clock divider generates a clock of higher period and lower frequency compared to the original source clock. A typical example of a clock divider is a 2-bit ripple counter. So let us try to understand this clock divider by using 2-bit ripple counter. So as we have seen, whenever frequency is getting reduced, time period will be increasing. Let us try to understand it by using an example of 2-bit ripple counter. So it contains two flip-flops, flip-flop 1 and flip-flop 2. For this circuit, if a period of a clock at the input of the first flip-flop is 10 nanosecond, so at clock I am applying 10 nanosecond time period I am taking, then waveform generated at the least significant bit is divided by 2. So here it will get divided by 2 and I will get the time period as 20 nanosecond. And again the signal which passes from least significant bit is applied as a clock to flip-flop 2 and the output that I get at most significant bit will again divided by 2, so it becomes 40 nanosecond. So overall it is divided by 4. So you can see here for the same design the waveform at the most significant bit is divided by 4, which means it has a period of 40 nanosecond. So whenever you are taking the initial time period as 10 nanosecond, at least significant bit it is getting divided by 2 and again it is getting divided by 2. So I am getting 20 nanosecond as time period at least significant bit and 40 nanosecond as time period at most significant bit. The same thing you can see in the example. This particular waveform you can see here. So here clock divider means frequency divider. Frequency is getting reduced means time period is getting increased. Now let us try to understand the waveform. So initially I am taking 10 nanosecond at clock. So it is getting divided by 2 at least significant bit. I am getting time period of 20 nanosecond. So here it is divided by 2. So whenever frequency is getting divided by 2, time period will get multiplied by 2. So that's why when I am taking 10 nanosecond at the clock, it is becoming twice, that is 10 nanosecond into 2, which is 20 nanosecond. And again after passing through flip-flop number 2, it is again getting multiplied by 2. So this 20 nanosecond will become 40 nanosecond. So here it will become 40 nanosecond. So that's why it is divided by 4. Whenever frequency is getting divided by 4, time period is getting multiplied by 4. So this is the example of 2-bit ripple counter. If you take an example of 1-bit ripple counter, it will function as divided by 2. If you are taking 2-bit, it will function as divided by 4. Now let us see how to write the constraint for it. So you can see here create clock hyphen period 10. Here 10 indicates the initial 10 nanoseconds of time period that we are taking, followed by name CLK, get ports CLK. So if you have not understood how we are writing this create clock, please check my first video on create clock. Next, we have to write generated clock at least significant bit and most significant bit. Create generated clock hyphen name least significant bit hyphen source. From where it is coming from? It is coming from CLK. So that's why we should write it as get underscore ports followed by CLK. Now we are dividing the frequency, so that's why I am using the switch called as hyphen divided by 2. So factor is 2. Next, I am applying it at this particular pin. So if you take any flip-flop, so it will have the following pins. This is D pin, this is Q pin, this is CK, that is clock pin. So as we are applying this at this point, this should be written as flip-flop 1 output pin is Q, that is pin. So get pins flip-flop 1 Q. If it is not clear, let us try for most significant bit now. So create generated clock hyphen name is most significant bit hyphen source. Now what is the source? This is a source, right? So where it is coming from? It is coming from flip-flop 1 Q pin. So this is a pin. So that's why we need to write it as get underscore pin followed by flip-flop 1 is the instance name and Q is the pin. Q is the pin of D flip-flop. Next, factor, that is divided by 2. Where this is presented flip-flop to Q pin. So this is flip-flop to Q pin. So that's what I've written it here. So let me make it simple. So here this should be written as flip-flop 1 Q and this will be flip-flop 2 Q. So for least significant bit this is source and for most significant bit this is source. So this is how we need to write the constraint for create generated clock. Now the same thing we can try by using edges. So hyphen edges, first one is rising edge, falling edge and this is the rising edge. So you remember this point, this should be first edge of the next clock period. So again this point will be same. Initially we need to apply clock here, so that will be done by using create clock hyphen period 10 hyphen name clock and get port CLK. Now we need to write create generated clock for least significant bit and most significant bit. Now we are doing this by using switch called as hyphen edges. So create generated clock hyphen name is least significant bit and hyphen source, from where it is coming from? It is coming from the clock. So it becomes get underscore port CLK. Now hyphen edges. So take reference between these two. So for least significant bit, this is the rising edge, this is falling edge and this is rising edge. So here this first rising edge is coming at 1. You have to take it with respect to clock, and this falling edge is with respect to this one, so it is 3. This rising edge is with respect to 5. So here edges will be 1, 3 and 5. So that's what I have written here, 1, 3 and 5. And this is nothing but flip-flop 1 Q pin. So get pins flip-flop 1 Q. Be clear with this. This is get pins. This is get ports. There is difference between pins and ports. Now let us write for most significant bit. Create generated clock hyphen name most significant bit hyphen source. So now this is the source, right? So this is nothing but this is coming from flip-flop 1 Q. So this becomes get pins. So get pins flip-flop 1 Q and hyphen edges. So for most significant bit it is with respect to LSB. As I am taking source is nothing but FF1 Q. So it is least significant bit is the source. So check the rising edge and falling edge with respect to least significant bit. So this is rising edge. This is falling edge. So this rising edge with respect to LSB is 1 and falling edge is at 3. So that's why hyphen edges is 1, 3. And the next one will come somewhere around here. So it is nothing but 5. Always make sure here odd number of edges we need to give. That is first one should be rise, fall and rise. Here this is important. This should be first edge of next clock period. And where we are applying this most significant bit, this is at flip-flop to Q pin. So get pin flip-flop to Q. Now let us write create generated clock command for most significant bit. Now it is with respect to clock. So here name is MSB hyphen source is get ports CLK. Now here source is nothing but this one CLK. Let us see the edges with respect to CLK. So for most significant bit we are checking edges with respect to CLK. So this is rising edge, this is falling edge. So with respect to CLK this is 1, this is 5. So that's what I have written here 1, 5 and the next one will come around at 9. And where we are applying this, this is flip-flop number 2 Q. So that's why get pins flip-flop to Q. So this is how we need to write create generated clock with respect to edges. So the next concept is clock multiplier, which is also called as frequency multiplier. So in frequency multiplier, whenever frequency is increasing, time period will reduce. So simply remember this relationship, frequency is inversely proportional to time period. When frequency is increasing, time period will decrease. When frequency will decrease, time period will increase. So frequency multiplier means whenever you are multiplying frequency, time period will get divided by the factor which you are using it here. Here I am taking as 2, so that's why I am getting here. Suppose if it is 4 times frequency means time period will get divided by 4. So clock multiplier, which is also called as frequency multiplier. A clock multiplier is a circuit where frequency is increased and clock period is decreased for faster clocking rate. This technique is typically used in microprocessors and on internal buzzers so as to improve the overall throughput of the processor and is generally used in conjunction with internal cache memories. So whenever frequency is increasing, time period is getting reduced. If you see figure 6.2, this is a simple clock multiplier. So it shows the circuit of a simple clock multiplier where the clock frequency is doubled. The circuit is simple implementation of clock and its delayed version. The delay can be introduced in the line by using buffers and inverters. So simply if you want delay, you can use here inverters as well as buffers. It is more common to use phase lock loop to achieve frequency multiplication. So here this is done by using an XOR gate. So for XOR gate, whenever inputs are same, output will be 0. If not, it will be 1. So first input is clock and delayed version. Whenever these two are given as input to XOR, I am getting output as CLK out. So let us try to understand this waveform. So you can see the same figure I have taken it here. Initially I am taking clock and delayed clock. So generally to get delays you can use either inverters or buffers. So this is a waveform which I am getting as delayed clock. So this is one input, this is another input. So whenever these two are given as input to XOR gate. So for XOR gate, it contains suppose two inputs A and B and output is Y. Combinations will be 0, 0, 0, 1, 1, 0 and 1, 1. So whenever inputs are same, output will be 0. If not, it will be 1. So by using the same concept, we'll get clock out. So here this is 0, this is 1. So inputs are different. So I'm getting output as 1. Next here this is 0, this is 0. Whenever inputs are same, output will be 0. And here this is 1, 0. Whenever inputs are different, output will be 1. And here it is 1 and 1. Whenever inputs are same, output will be 0. By using the same concept, you can get the output waveform, that is clock out. Now let us see how to write the constraint. So this part will be same. Please check the previous videos on create clock. So I'm taking a time period of 10 nanosecond here, that is at clock. This is the clock. Now I want generated clock at CLK out. So create generated clock, hyphen name is CLK out, hyphen source. From where it is coming from? This is coming from the clock port. So that's why hyphen source get port CLK, and here I'm doing multiply by 2. So hyphen multiply by is a switch and 2 is the factor. And where I'm applying this? I'm applying this at the pin of XOR. So if you take XOR gate, here two input pins are A and B, output pin is Y. So you can take it like this. So here input names can be anything. So here in our example I am writing here as Z. Why? Because here this pin instead of Y it is Z. So that's why it should be written as get pins. XOR 1 is the instance name of it. That is XOR 1 followed by Z. So let me draw it clearly. So this is something like this. XOR 1 is the instance name and Z is the output pin name. So that's why I'm writing here as get pins XOR 1 Z. So this is the instance name. This is the pin name of the XOR gate. Or else you can give it like this also. Everything will be same followed by hyphen switch duty cycle. So generally here hyphen cycle 50%. So here I'm taking duty cycle as 50%. Means the time period for which it is on divided by total time period. Means it will be equally on and equally off. So on time period, this is off time period. So this is how we write the create generated clock constraint for clock multiplier. Now let us see what is meant by clock gating. So generally this clock gating comes into the picture whenever you want to disable the clock for some portions of the block within your design, so that it helps in power saving. That is, dynamic power consumption can be reduced. So coming to clock gating technique has become very popular since mid 1990s to reduce power consumption. Power in a circuit is consumed when a flip-flop or register in the design switches state due to clock trigger. So whenever clock is getting triggered, it leads to on and off. Suppose if you take an example of an CMOS inverter, let me draw the diagram of CMOS inverter which contains one PMOS and one NMOS. Here top will be VDD and here bottom will be ground. Here this portion will be input, this will be the output. So generally some capacitor will be present here. So whenever you are applying inputs, that is whenever input is equal to 0, this will be on and this will be off. So whenever it is on, it acts as short circuit. This leads to charging. So capacitor will get charging. Similarly, when you are applying 1 at the input, it will get discharged. So charging will happen from PMOS and discharging will happen through NMOS. So this is nothing but switching activity. Whenever input is getting switching, this leads to charging and discharging of capacitor. So because of this leads to some dynamic power consumption. So however, in a design portion of the logic may not be getting used at certain times. So by using this particular clock gating concept, what we do is, if some part of the design does not require clock, so generally in order to switch it off, we'll make use of this particular concept. So during that stage, disabling clock to those portions of the design reduces the switching power. This is achieved by having enabling logic before the clock, and such a clock is called as a gated clock. So generally it will be done by using some AND gate which contains some clock followed by enable, so that we get output as some gated clock. So whenever it is not net, so depending upon the enable pin, clock will be given or else clock will be disabled. So generally enable pin can be either 0 or 1. So if you see the figure of a gated clock, it will be something like this. So this is a flop and here I am doing gated clock by using an AND gate. So this clock is getting controlled by the enable pin. So here if you see figure 6.3 shows the example of a gated clock. We can also use clock gating to obtain divided clock with waveforms similar to those of figure 6.1. So this concept we have already seen, like 2-bit triple counter. Like initially at LSB we are getting divide by 2 and here I am getting divide by 4. So let me write here, I will get divide by 2 and again here divide by 2. So overall it will become divide by 4. So the same concept can be achieved by using this gated clock. So the concept of clock gating can be extended to create clock pulses. So let us see the figure 6.4 where the clock is gated via a chain of odd number of inverters. So here this is the same diagram. Here for the sake of delay you can use either inverters or buffers. So here we are using 3 inverters which are connected back to back. Depending on the delay on the chain of inverters, a pulse will be generated. This method is used to improve performance and reduce power as well. It is important to ensure that clock gating is typically done with only one clock. Now let us see what is happening with this. So if you see the figure, a gated clock to generate pulses. So we need to apply some clock and the delayed version will get applied to the another pin of this particular AND gate, and by using that we'll get the pulse. So simply for one AND gate I am applying one input followed by here I am giving some delay and I am applying another input, so that I am getting output which is nothing but a pulse. So this is the clock that I am applying and this is the delayed version, like it is getting delayed by using 3 inverters. and I'm getting some pulse. So simply you can use a function of an AND gate for an AND gate which contains 2 inputs and 1 output. So 0, 0, 0, 1, 1, 0 and 1, 1. So this is the truth table. So you can check here whenever this portion is 0 and this is 1. 0 into 1 will be 0 and here it is 1, here it is 1. So 1 into 1 is 1. So it is going high. Next here it is 1 and 0. 1 into 0 will be 0. So by using this you can get the pulse which is shown here. Now let us see how to write the constraints. So generally this portion is common. I am taking a time period of 10 nanosecond. So we have to write create generated clock command for this particular pulse. So create generated clock hyphen name. This is the name pulse hyphen source. From where it is coming from? This is coming from the clock port. So get port CLK. Now we are writing it by means of an edges. So here check this pulse with respect to CLK. So here I am getting one rising edge, here one falling edge, here one rising edge. This rising edge number is 1. This falling edge number here as nothing is there. So obviously here also it will be 1. And this rising edge number is 3. So simply edges will be 1, 1, 3. So that's what I have written here 1, 1, 3 at the edges. Next get pins. AN1 is nothing but instance name for that particular AND gate and Z is the pin name of AND gate. So here also same concept is applicable. This is A, this is B, this is Z. So 2 inputs and 1 output. And here AN1 is nothing but the instance name. So that's why I'm writing here as get pins, instance name followed by the pin name. You can ignore this last line. Now let us see few more examples. Now make a note of this particular design and waveform and try to write the constraints, so that it will become practice for you. So let me explain. Initially we need to apply some clock at CLK. So create clock hyphen period 10 nanoseconds hyphen name CLK get ports CLK. So I'm applying a clock which is having a time period of 10 nanosecond. Now I want create generated clock, that is at GCLK and GCLK2 I need to write this particular constraint. So create generated clock hyphen name is GCLK hyphen source, it is coming from CLK. So get port CLK and it is nothing but divide by 2. Why? Because you can see this particular waveform. These are the rising edges. So it is being high till here and going low and again this repeats. So hyphen divide by 2 get pins flip flop 1 Q. So this should be written as flip flop 1 and Q. Here also it will be like flip flop 1 and this is something called as Q bar. But the difference here bubble is there. So you have to use one extra switch called as invert if you are writing for GCLK2. So see here create generated clock hyphen name GCLK1 source coming from clock divide by 2. It is at pin flip flop 1 Q. Next for GCLK2 source is same divide by 2 and hyphen invert. This is very important. Why? Because there is a bubble. If you observe here there is a bubble which is inverting. So hyphen invert get pin flip flop 1 Q bar. So simply this is the nomenclature which I am following. This is D, this is Q, this is Q bar and this is CK clock pin. So this is how we need to write the constraint for this particular design. Now let us see for this particular one. So you can see here this is negative edge. So positive edge is something, it will be like this. So let me draw it clearly. If you take one flip flop, this is D pin, this is CK, this is Q, this is Q bar. If it is negative edge trigger, then there will be a bubble outside. This is CK, this is Q, this is Q bar. So the previous example which we have seen is positive edge trigger clock and now which we are seeing is negative edge trigger clock. So first apply clock. So create period hyphen. So command is create clock hyphen period is 10 nanosecond hyphen name CLK get ports CLK. So here I am applying a clock which is having a time period of 10 nanosecond. Now we have to write generate clock command for GCLK3 and 4. Now this we are doing it by means of edges. So here this should be written as flip flop 1 Q and this will be flip flop 1 Q bar. So create generated clock hyphen name GCLK3 source coming from clock and edges. So compare GCLK3 with respect to clock. So here I am getting rising edge, falling edge, this is rising edge, this is falling edge. So rising edge is at 2, falling edge is at 4 and again so here somewhere it will be 5, this is 6, so it will be 6. So 2, 4, 6 are the edges. 2, 4, 6 rise, fall, rise and get pins flip flop 1 Q. Next create generated clock hyphen name GCLK4 coming from CLK and edges. So if you see edges between CLK4, GCLK4 and CLK. So this is rising edge, this is falling edge, this is rising edge. We have to check it with respect to CLK. So this is 4, 5, this will be around 6, this will be 8. So edges will be 4, 6 and 8. So edges are 4, 6 and 8 and it is flip-flop 1 Q bar. Here we are not writing hyphen invert. Why? Because this is negative edge trigger and we are writing it with respect to edges. So if you are not writing it with respect to edges, then you have to mention as hyphen invert. So here directly we are using edges, so there is no concept of hyphen invert here. This is very important example. You can see here two clocks are there, C1 and C2, and I told you whenever multiple clocks are there, we need to use a switch called as hyphen add. If you won't write this one, suppose if you write a constraint for C1 and next if you write the constraint for C2 and you forgot to add hyphen add as a switch, then this will be overwritten. So be clear if there are multiple clocks. So let us write the constraint. So create clock hyphen name C1 time period. So here this is 10 nanosecond. Get port CLK and C2 is 15 nanosecond and I am writing as hyphen add. Remember this. Now write generated clock. So GC1 and GC2 I want. So create generated clock hyphen name GC1 and here I am dividing it by 3 and source it is coming from get ports CLK and in this among C1 and C2 the master is C1. GC1 is with respect to C1, GC2 is with respect to C2 and here GC1 this should be as flip-flop to Q pin. This is the Q pin and instance name is FF2. Next create generated clock hyphen name GC2. Again I am dividing it by 3. Source it is coming from get port CLK and here master clock is nothing but C2 and here for GC2 it should be written as flip-flop to Q pin and here add the switch called as hyphen add. So for this particular design it should be written like this. So separately we'll see the examples with respect to edges now. I've taken the same example of divide by 2 waveform. Now we are writing the constraint by using a switch called as edges. So if you are dividing frequency by 2, time period is getting multiplied by 2. So initially I am taking time period as 10, so it is getting multiplied by 2, it becomes 20. So you can see here the time period is increased to 20 nanosecond. Now write the constraint for this by using hyphen edges. So create generated clock hyphen name. So some name I am giving as gen clock and hyphen source it is coming from CLK. This is CLK and edges. So here rising edge is at 1 and this falling edge is at 2 and this rising edge is at 3. So edges will be 1, 2, 3. Edges are 1, 2, 3 and get pins. At what pin you want to apply that pin name you have to give it here. Now see the example of divide by 4. So frequency is getting divided by 4, so time period is getting multiplied by 4. So time period if you are taking as 10 nanosecond it is getting multiplied by 4, so it is 40 nanosecond. And mainly see the edges. So here this is rising at 1. Here it is falling at 3 and again it is rising at 5. So edges will be 1, 3, 5. So edges are 1, 3, 5 and the remaining constraint command will be same. So thank you. So in this particular video we have understood how to write the constraint for create generated clock. Please stay tuned to my channel for the next constraints.